Okay, so here's a couple of trivia things for you guys. So as we're standing on a mountain, right? And we just climbed the summit or something, and all of a sudden we notice this major temperature change, right? What causes the temperature change? I was hoping I could, draw on the whiteboard. I'm sure Steve knows that.
Just higher altitude, colder air temperatures.
Okay, what makes the air colder?
Less density of air molecules.
Okay, less density, less kinetic energy. So you know that, right? Yeah, sure you do. All right, you're familiar with that concept, right? Mm-hmm. Okay. All right. Good. Hold that thought. Now, you go deeper in the ocean, right? You go deeper in the ocean. Okay? All of a sudden, the water at the surface of the ocean, for example, is a lot warmer than the water towards the depth of how many thousand feet you're talking about, right? Mm. What happened to our principle? Our density principle.
Well, you're at a much higher pressure, for one, and there isn't as much penetration of the sunlight.
There's a much higher pressure, which would do what?
PV equals RP, so increase the temperature.
It should increase the temperature. It should increase the temperature. But why doesn't it?
Doesn't it? Actually, that's why the fish actually live in lakes. But I don't know how it does in oceans.
Mm. Not when you go really deep.
Steve, are you familiar with that?
I'm not familiar with.
It'd be cool if we had a board, but I can show you the gradients. But so as you get deeper, the ocean pretty much follows what's considered the geotemperature gradient. Are you guys familiar with that? There's also a lithographic gradient. Are you guys familiar with that?
No.
And just let me find out what's going on. Anyway, that's an interesting concept, right? Do you know what the answer is?
No.
Okay, it has to do with the sea swells and the fact that the ocean currents always move the colder water beneath and the hotter water above, which leads to another question. But hold that thought. So here's a question for you. As you go down the temperature gradient of the Earth, right, you increase the temperature. You increase the density of the molecules, right? All of a sudden you have the weight of the Earth on top of you, right? Incidentally, and the temperature goes up. It unilaterally goes up. There's no exception to that rule in the Earth, right? Okay. But in the oceans, it essentially violates the principle. And so, if you're going to have this mixture of, for example, a miscible front, where, different compositions mix, right? You need something to describe it. And that would be what is classically known as the diffusivity equation. Right? And I'm sure Sai has seen it and knows it backwards and forwards because it's very common in porous medium migration. All the hydrologists use it, all the petroleum engineers need it, the geothermal engineers are very conservative. So, as the temperature gets thicker, right, as you pile this earth on, what is actually heavier? Were you familiar, for example, that what weighs more, a Volkswagen or a cubic yard of water? Would you say?
The Volkswagen.
A Volkswagen weighs more?
Depends which Volkswagen you're talking about.
Is that true?
Yeah, because it's 1 cubic meter or kilometer.
One
Well,
cubic
it
yard,
depends
but
on
it's close to
actually the
me.
molecular structure and how densely packed they are.
But
as well.
if we even assume that it's salt water and then we use the salt water density, even then it depends on which Volkswagen you're talking about.
Okay, so when you mix, how do you model mixing brine water with fresh water? Is that a concern, would you say, for hydrologists?
Yeah.
Obviously, right?
We use it in chemical engineering because they separate.
Yeah, stratified. It's
Exactly.
salt brine water is lighter
Exactly.
than actual water, right? The fresh water.
Absolutely. So actually, I do have this. A yard of cubic water does actually weigh more than a Volkswagen. It's weird, isn't it? That is weird. But what? So let's extrapolate that one and say. So now let's take a yard of earth. Which one weighs more? A yard of water or a yard of let's say barite or natural soil or refined. What's that?
Earth would weigh more.
What's that?
Earth would.
The
weigh
Earth weighs way more.
Yeah.
Would you say way more?
Yeah.
Okay. What is the specific gravity of water?
1.
Sai would know that. Of course.
1.
Sharia would also know that. You're a chemical engineer, right? Yeah. What is the specific gravity of barite? Natural dirt.
I don't know.
Well, generally it's about 1.6. So, at 62 pounds per cubic foot, right? You multiply that by 1.6, and that's how much the Earth actually weighs. And that is what comprises the lithographic gradient. So you have the geothermal gradient, which it dictates according to a specific gravity of 1, and then you have the lithographic gradient, which is essentially mostly what the Earth, as you go deeper, follows. And so I can show you some of those things, but isn't it ironic that? So let's see, I had them and then I had to reboot. So that should be there. So the gradients. Okay, so here is the surface gradient. Normally, a good rule of thumb is that per 2,000 feet, you increase about 1,700 Celsius. That's about the temperature gradient. So when you consider that, what happens to the pressures?
What do you mean?
What's that?
What do you mean?
So does pressure, the internal pressure of the Earth, does it follow the temperature gradient? Is it inversely or unilaterally related to the temperature gradient?
Unilateral?
Exactly. They coincide. They're very close. This is all the way to the inner core of the Earth at 7,000 Kelvin. But everything that the hydrologists deal with is way up here, and everything the energy side is dealing with is just a little bit deeper in respect, right? But that's interesting. So you have different miscible fronts. There you go. So as you go even deeper than the ocean, right? Then you have your different gradients. See here, there you go. So lithographic, and then if you add alternative fracture, the pore pressures, and hydrostatic. What it tells you is that you'll get bigger pressures as you go deeper than you will based on your hydrostatic head. Do you understand the concept of hydrostatic head?
No, not exactly.
Hydrostatic head is, do you know what it is, Shamil?
been a long time since I've had to.
I know sinus.
Like the vertical depth of water.
Yeah, the hydrostatic head is the weight of the water above you, the vertical weight. And you remember Bernoulli's equation? The sum of all the pressures has to be zero.
Sure.
So that's the hydrostatic, and this shows how that increases with depth. And lithographic, which is your specific gravity of 1.6 times bigger, is about follows pretty much a linear curve. And so interesting. All right, so moving on. Here's another example. But if I flash temperature or pressure up here, they both look very similar towards, okay. So those things are interesting. Now, all I wanted to do there was show that, and then let's see, tabs with respect to the diffusivity equation. Do you guys? So when we model a reservoir, a water reservoir, an aquifer, and if you're working for the state of Washington, you're very concerned about fresh water and the runoff and the replenishment of water resources, right? If you're an energy engineer, right, you're concerned about usually much deeper than that, much higher temperatures and pressures, and you're also concerned with how to model, this environment, in situ condition environment. Well, so my thought is there are several ways that scientists have figured out to model that. One of them is finite elements, and the other one, as far as building math models, and another one is called finite differences. And I've tried to, I'm just playing around with Python and everything. I've tried to do the finite difference one. I'm getting more bold to try to take on elements. I actually did study it in school when I was in it many years ago. But you probably did too, right?
I'm not sure. The finite differences?
Yeah, did you do elements?
Mm-mm.
Yeah.
Finite difference is nothing but the average of two at least.
Yeah.
Yeah, the finite differences is what's the main one? The center step. What's that?
Central difference?
Yeah, FCTS or something, right? Anyway, there's libraries for that already in Python. There's also libraries for the element method in Python already, and I've been playing around with them. I'll just show you where I'm at so far. Like I said, I'm trying to get better at this. But here are so when you're concerned about modeling this process in the Earth, right? You get reduced to the diffusivity equation. Now, aside, does that look familiar to you? That equation?
I mean, the partial differentials are, but I don't work with the same equations.
I mean, do you have
But
that?
they're similar.
You have that same porosity, viscosity, compressibility relationship?
No, I don't
You
work
get-
with them, but they're like with the similar.
Anyway.
Are you in the spherical coordinates?
What's that?
Are you in spherical coordinates?
Well, this would have been spherical coordinates.
Yeah, see, that's right.
That's single dimension.
We work with rectangles. Yeah.
Yeah, well, it's similar.
Yeah, this is.
So the diffusivity equation is really measuring whatever you're considering. I think it arose out of the study of heat. Okay, mechanical engineers would know about that. And if for example the gradient, the change in temperature with respect to the medium is linear, then you have like, let's say right here, as the change in temperature, it creates like a front as it dissipates through whatever the medium is. Like, let's say you put a hot iron on this side of the table and you want to see how long it takes for it to get over there, right? And it sort of goes in a linear path, right? So that would be the change in the distance with respect to the change in time. But it's usually how they model, because the change, it's the change in the change of distance, which invokes a Laplacian treatise on the distance as it changes with respect to time. So do you know about Laplacian forms, right?
Vaguely, yes.
Okay, so they are simply the second order evaluation of the change in change of whatever you're evaluating. Okay, so but now you want to do that with time. Now let's say it's nonlinear. Let's say you want to see how fast the temperature accelerates, or you know it's a mess. You know it does this, and then it becomes a second order partial differential with respect to both sides, with respect to time and distance. So the very simple equation is the change in time with respect to the change in one direction, the change in direction. So it's the change in time with respect to the second order treatise of the change in distance. That's the simple form of, and when you extrapolate that, Darcy sat there and watched it happen in a porous medium, and he built some parameters which were permeability. Now there are other parameters. There's connectivity. There's but mainly it was the pore space of the medium, the connectivity of the porosity of the medium, the permeability. What's that?
Hydraulic conductivity. If you look at
the hydraulic conductivity, the compressibility of the medium of the fluid that you're evaluating, and the viscosity, resistance to motion, to movement of what you're evaluating. So if you're treating a mixture of oil and water, that's different than if you're treating water and if you're treating just oil, just some kind of hydrocarbon derivative, right? So those were all the studies are related. And here, I think this is how it is, but this is diffusivity heat equation. It looks the same, only all the constants are different. So now, this would be a task, but I'm not going to do it for you. But you can actually derive, if you plug this equation into the second, and you come up with the first equation, which is the evaluation of the diffusivity equation. So let's see, minus, there it is in simple form, as you operate on x and t. Okay, which is, and this, I don't know, we're familiar with this. That's just a very, something that's very recognizable. I think the hydrologists use it as well. But now, Navier-Stokes, on the other hand. You're familiar with Navier-Stokes, right? Navier-Stokes said that, okay, instead of treating it as a potential, so when you talk about the diffusivity equation, you're talking about pressure, okay, a potentiometric difference, right? And when you treat the Navier-Stokes equation, includes an energy balance, a force and momentum balance, and a mass balance, all piecewise linearly incremented over a boundary. So you're solving all three of those equations at once and you use the characteristics of each of the equations to describe whatever the reservoir is or the aquifer. And because I know the hydrologists I know they have big conferences on using finite elements. I've even looked at their stuff. I cheated.
I'm going to talk about that.
Yeah, see, he's going to talk about it. So anyway, but that would be the Navier-Stokes. And here are some pictures of the Navier-Stokes series of equations. And I'm getting bold enough to try to do it myself in finite elements. But so you have a continuity. You have continuity. You have momentum, and you have kinematics, which is your energy. And these terms, like your T and your D, go away when you compile this thing into. But that pretty much follows the way you guys treat it, right? The hydrologists treat it, yeah. So here are the different terms in an energy balance in Navier-Stokes. Yeah. So it's all there. Anyway, so very briefly, although my code is not, I'll just show you what I've done so far, which is And if, okay, keep going. Where's that? Where'd it go? Okay. Okay, so this here, I tried to, it doesn't work. I tried to map the difference between using an analytical solution and a numerical solution, and it's broken. It doesn't show it very well. And then I extrapolated that to, well, this is not the real. I wanted to extrapolate it if I get 2 dimensions into spherical coordinates. So I haven't actually done it yet. I just know I can get it to work if I finally.
Is this output from your code?
Yeah, this is my code. Yeah.
What do you use for plot?
I just use Matplotlib in Python.
Matplot3D.
Matplotlib, yeah.
Yeah, but what's the command?
Oh, and then you got to build your little graph, in your axes.
No, for this one.
Oh, for this I use polar coordinates.
Right. And what's the matplotlib command? Plot3D or?
Yeah, plot3D.
Okay.
But this isn't really real. I just messing with it because I want to be able to do it at some point. But I'll have X and Y against whatever I'm using. So if you want to see what I'm doing, and it's kind of broken, like I tell you. So anyway, that should have stopped. Control. Okay, wait a minute. Let's see. Did I know. Okay, but if I come back. If I'm in some kind of editor, yeah, it would, but, escape and quit. So I will tell you what I'll do. I'll shut that down. I'll go over here. But what I wanted to show you is part of the numerical modeling thing, which is what I'm trying to do, which might be worthwhile. I don't know if you... Hey, Sheree, did you know where the bathroom is?
No, but actually I'm over.
Oh yeah, get some Pringles. There is actually a bathroom down there.
Okay.
Okay. So let me get back to my code here. So if I go to code and I get here, I had to move all this stuff when I got here. So I'm going, and then let's see. One of these I did have ready to show. I am actually. I'm actually my differential equation. I think it's right there. So show in. Here we go. Diffuse Python. D. How about that? And then I think show 202 dash sh. This should work. I think M, right? Yeah, M. So you probably use Python, right?
No, I use Anaconda.
Oh, you use Anaconda. My thing is, my engines are so wimpy. I just, I just want to keep as much memory free as I can. Okay, so here you have it. This, I'm evaluating U and UX on different places, and I'm incrementing through, and this is the resolution of the matrices, and I'm using a delta time, a delta X, a delta Y, and I'm evaluating the charge, and it doesn't show much changing there. I need to add some parameters, but just to show you that at every step it evaluates and then I get a thing on how long it takes me to process it and stuff. But that's the nuts and bolts of it. And so anyway, at this point, trying to solve the diffusivity equation in Python, and I'm actually trying to do it myself as much as I can without using all the already prescribed Python tools, because everybody else has done it and they probably did it better than me, But at some point when I have my own tools working, I can. I have built some apps, and I'll be able to claim it. But so anyway, here's so I built some little stupid things like this one is let's see, this is this is a statistics app. It's got, and what it does is it lets you evaluate P and Z values for. And so for kids or students who use this, usually they're trying to get through a statistics class, this is a great way to get to the answer real quick. And and so I can run that for you, but it doesn't have much to do with diffusivity. And then I compute confidence levels and things for them and stuff like that. If you want a copy, it's you can easily download them. I'm happy to share it with you. Do you use statistics much? Yeah. See. Anyway, just one of the ones that I did do that I did dimensionless pressure. Now this one, again, it's kind of the old logo thing. It's not exciting, but you can do engineering calculations. But here is dimensionless pressure, and what you have to do is you have to have meaningful values in stuff. I'm going to try to do it. And then you compete, let's say you had a 35 porosity capability, and then you had, so I need to compete a dimensionless time. I competed a dimensionless time. Then I try to get a dimensionless pressure.
You're doing a ratio?
Well, does anybody know what the advantage is of dimensionless pressure? Do you know? Yeah.
You don't have to deal with units, one, and then the other one is like you have a comparison to something that makes sense. Instead of comparing to stuff, you have a comparison to one thing, like specific gravity, for example.
Right.
So it's all related to water.
So is it like specific gravity in that it's a ratio?
Yeah.
Against a standard?
Yeah. And then you use it in the equations, you don't have to be confused about it.
Okay, so then I computed dimensionless time based on those reservoir parameters, and then I compute I get my pressure based on what the time you selected, and it tells me. So I had a drop, for example, in that case, whatever it was. If you're at 754 seconds out or something, you'll get a drop of 23 psi over. So that's based on these parameters of levels of production. It works the same for water wells, kind of thing. That's true. So why is dimensionless? He explained it well, but what I was thinking is, so why is that advantageous? When would it be more advantageous to have dimensionless pressure if you're concerned about what?
An effect when you're looking at relative, when you're comparing them.
Exactly. And at least the way I understand it, it has a lot to do with boundary conditions.
Oh, yeah.
So that, the boundary conditions don't change your problem. Because you can assume, for example, right? I showed you the gradient, right? You can assume you have infinite pressure. But as you produce a water well, for example, right, you don't have infinite pressure. You don't have it. There are boundary influences, right? If you deal with hydrocarbons, the effect is much more pronounced. So, and if you're the guy that's making $1,000 a day, and your job is to flow that thing, because right now they're paying top dollar for, then you don't want to flow to the point that you essentially collapse the well, right? That you collapse the well bore where the oil interfaces with your capacity to lift it, right? So you have all these concerns. So you want to be able to model something that doesn't that isn't dependent on the boundary effects. Okay? So you can say, okay, to this point, I'll always have a replenished pressure. But as soon as I get to where I feel the boundary effects, I won't. I don't have them, see? And so that's a concern. So dimensionless pressure is used in these kind of computations. Anyway, I was just going to turn the time over to Zai. And,
How are you guys doing on that? Yeah. You guys are fine?
Yeah.
Okay. So I was